moving into commercial ventilation. After we're talking about envelopes and trying to keep the buildings tight. The textbook I had my students go through this year is A House Needs to Breathe, or does it? The house or commercial building does not need to breathe, but people still do, right? So we don't want to build leaky buildings, but we do want to have good ventilation systems. For those that aren't familiar with the Integrated Design Lab, I'm glad that you're here, and feel free to just reach out to us online at idlboise.com. But we're part of the University of Idaho. These lectures are sponsored by the Northwest Energy Efficiency Alliance and the Better Bricks program. So there's a lot of great resources available there. But I want to kind of move into code requirements specifically for Idaho and looking at 2018 versus 2024. There was a vote this last year. There was push from fire officials and industry to update Idaho's overall building codes for consistency and language and compliance, and particularly on fire safety front. So what's still on the books in Idaho right now is 2018. What we are considering moving to, and had a lot of discussion on this last year, is leapfrogging the 2021 and going to the 2024 with amendments. I will say there's not too many amendments on the ventilation side or the commercial side that IDAPA in the IDAPA rules at this point. We're not about to switch to 2024. The legislature will vote on it. The Division of Building Safety kind of oversees, though they've got a board, a bunch of different stakeholders. They all vote on what's best for Idaho based on consumer feedback, and then they give their recommendation to the Division of Occupational and Professional Licensing, which then gives their recommendation to the legislature. So at this point, there was a unanimous vote to move to the 2024 code with amendments that the legislature will hear in this next session. If they adopt it, then in 2027, a full year and change from now, Idaho might adopt the 2024 code. Okay, but for now, we're still on 2018. So what I'll talk about in the next hour is kind of general ventilation requirements, economizers, demand control ventilation, and energy recovery ventilation, and then parking as well. And there's this tension that occurs, right? I said that the council that voted on this was this Division of Building Safety. Fresh air is great to breathe. And a great way to breathe fresh air all the time is to have like no walls, no roof around you, right? But if we have that, then that takes a whole lot of energy to heat your building if windows are open all the time. And the hope is to improve the health, safety, and welfare, including financial welfare of building occupants. So the more fresh air you let in, the more you have to condition it, which spikes your energy costs. The less fresh air you bring in, the more possibility you have of poor indoor air quality and potential health effects. So how do we balance this tension, right? How do we make sure that we don't have super high carbon dioxide levels, which probably don't harm our health, but certainly affect our concentration, and get out, bad smells and pollutants and things like that. So when you look at the ventilation requirements in the energy code, it's actually not in the energy code. There's requirements to control it well, but the actual amount of fresh air that you're bringing in to a space refers to the International Mechanical Code, which is also considering being updated from 2018 to 2024 for Idaho. And that really varies depending on the building type and then the occupancy. And it's this It's called the ventilation rate procedure. It also refers to ASHRAE 62.1, which is a good resource, good standard to purchase. Or if you're an ASHRAE member, you can access it free online under the read-only versions, where you're adding up essentially how many people do we have in there per square foot, and how much fresh air do we have to deliver to them for their activity. So if they're a kid and they're learning, they need a little bit more fresh air than us boring folks that sit in offices behind our computers, right? So kids get more fresh air than office workers. And then it also depends on how that space is being used. There's this area outdoor airflow rate in terms of cubic feet per minute per square footage of occupied room, right? And you add those two up together. There's also another column which isn't used too frequently, but if you do have contaminants in a space, for example, vehicles in a garage, then you do have an exhaust airflow rate that might be required to just pull some of those particulates out. This is just a small sample of the table. You can go online to the link there, or just Google International Mechanical Code and look up the specific ventilation requirements for it. It kind of follows 62.1. And what's kind of the why of this, and how do we meet it? I like to think of this as 4 or 5 different ways of dealing with a skunk. I opened my class this last year by saying, you could design as an architect or engineer, most beautiful home or building, but if people walk inside on this grand day of opening, right, you finally seen your designs that were on CAD realized, and you get to walk into the space, nobody's going to appreciate it if there's, a dead raccoon in the attic, or some really nasty smell in the space, right? This last summer, I had some raccoon visitors in Canada, my father-in-law's wood shop, who decided to make a home up in the attic. They're very cute and very, very smelly. So that was awful. So what do we start with? Removing the raccoons, right? Making sure that we got them out of there, somewhere else they can live free and happy in the orchard. So the first thing is just source control. You hopefully don't have a raccoon problem, but you might have trash, or I've seen a number, like 4 different police, sheriff's facilities that have all had evidence lockers, which had very smelly contraband in them, that then got vented into the rest of the space, right? So you want to isolate that and just get that out, right? So number 1, just source control. And number 2 is containment. This could be filtering. This could be changing the ductwork, right? We're fencing in the stuff, okay? Number 3 is demand control, right? Get an alert when you've got a skunk in the building. Or if we don't have a skunk, maybe we have an alert for high carbon dioxide levels. Carbon dioxide is not a poison. Our bodies can handle a lot of it, but neurologically, we are wired to be sensitive to that. So when we get high CO2 levels in a space, we start getting drowsy, our blood flow changes. It leads us to think that the place is stuck, right? And it can be kind of a proxy, an indicator that you're not getting enough ventilation into the space. So demand control ventilation is kind of measuring, it's doing that air sniff test, if you will, and saying, do we have high CO2 levels? If so, great, let's get that stale air out and bring more fresh air in. But we don't need to do that all the time, particularly in like a room like this. We've got pretty light occupancy in here right now, but if we had a full like Christmas party or something like that, where we've got a lot of people, at that point, we want to kind of, ramp that up and transfer the air out, right? bring fresh air in, get old air out. And then make sure that we are delivering that effectively. It's not just a certain CFM, cubic feet per minute. It is effective delivery in the breathing zone. If we've got a big vent in the closet over there, it's not going to help Dylan and Lee and I out a whole lot, right? So making sure that you are effectively, just pulling the air away from the skunk, the trash, smelly bathroom, or whatever. A great way to do this is through, underfloor air distribution, which we have stairs upstairs in this room, in this building rather. Displacement ventilation. So instead of just mixing all the air, it's having a clear direction of fresh air coming in at either from bottom to top, which is very effective thermodynamically, or one side of the room out to the other side. And a dedicated outdoor air system is a great way of doing this, right? You're not recycling air, you are constantly ventilating from one side and exhausting from the other side. And how much air do we actually need for breathing? It's a quick kind of example, and this is again on the residential side, but this also applies to multifamily, is to look at the area and either the number of bedrooms or for multifamily or residential, or in commercial situations, it's just kind of floor space. You've got a multiplier there. You add that up and you get a total CFM of how much outdoor air you need. To deliver this in a house, 90 CFM, you could get away with a pretty small, about a 4-inch diameter duct. With a forced air system, around your furnace, you've generally got like a 2 foot by 2 foot, like 4 square foot area that you're moving a lot of air through. But that's not your breathing air, right? That's just air that you're kind of recycling and heating up or cooling down. How much air we actually need for breathing? Very, very small. This is for a whole 2,000 square foot house, right? Just one 4-inch duct. Okay. So that is where kind of the advantage of dedicated outdoor air systems come in, because instead of trying to use a forced air system where we're heating up or cooling down this big quantity of air with big fans, instead we've got just a little bit of ventilation air coming in from one side. We've got exhaust going out either through bathrooms or kitchen or just the other side of the house. And we do our heating and cooling some other way, like mini splits, heat pumps, DRFs, something of that nature, right? And that way we bring in less outdoor air, so we don't have to condition it quite as much, but we still get comfort and we still get health. So how do we get, these kind of minimum ventilation techniques? This is kind of what the energy code is pushing us for. How do we get the skunk out? How do we fence in the skunk? How do we have an alert when there's a skunk in the place? How do we move the skunk air out and fresh air in? And then how do we make sure that we are blowing the air right over the skunk and getting it out, right? And it's not just skunk, it could be carpet fumes, it could be, OSB or anything that's built out of PRF, polyrenal formaldehyde. Formaldehyde isn't great for the human body. And when that off gases, we want that out. Okay? There is another way to figure out how much fresh air you need. So what's typically done for engineers is the ventilation rate procedure. And that's what I just kind of walked through for that house and the tables that I showed from the International Mechanical Group. So it's this kind of standard table, and it's based on area and occupancy. But there's an alternative that is also in ASHRAE 62.1, but it's rarely used. And what it does is, instead of saying, okay, we're just going to use general numbers for amount of outdoor air that we need to bring in, instead, we're going to target the skunk. We're going to look specifically at what contaminants are in the space and how might we scrub the air so that we don't have to bring in quite as much outdoor air. Instead, we're going to kind of treat the air inside the space through a separate system, or kind of a combination system. So we still bring some fresh air in, but a lot of what we're doing is kind of like filtering, scrubbing the air so that we don't have to bring in quite as much. That can really reduce the amount of outdoor air required by up to 50%. We did a study on that this summer where we were looking at a daycare facility that was about 10,000 square feet, and it had 7 different RTUs, and we looked at the energy and financial costs of using the standard ventilation rate procedure. We've got a certain number of kids and a certain square footage. Here's how much outdoor air we need. Versus what if we added some air scrubbing in there, get all the cuties that smells out, right? Some carbon filters in there, some high-end MER filters, so that we don't have to bring in quite as much outdoor air. We found that it would save, for this particular facility, about $1,700 a year. That was looking at pretty low energy costs that we have here in Idaho. This was gas furnaces. If you were in a place where you relied on propane or electricity for heating, say Grangeville or Salmon, those savings could easily double, right? So it can make sense to, instead of just using that standard table, use engineering to do the indoor air quality procedure for some additional scrubbing. I think this got more attention post-COVID. People have just kind of become aware of it. It's always been you've always had the option to do this, but few people have taken them up on it. Locally, Dan Russell has become a bit of an expert on this. He introduced me to it this last year. And he's pretty heavily involved in the ASHRAE kind of indoor air quality scene. So he'd be a good local resource to talk to. It's very helpful and has a heart for education, which I appreciate. Okay, so we've got to bring in a certain amount of fresh air. That's kind of like separate from the energy code. Just know that you need to bring in fresh air. How do we then control it? There is a requirement in C403 to add an economizer. And an economizer is, it's basically using free air conditioning. It's particularly helpful during the summertime and in dry climates like we have here in Idaho, climate 5B, climate 6B, where we've got these big temperature swings, right? At night, it really cools down a lot. And in the daytime, in July, it will really heat up. But we've got like a 30+ degree temperature swing. So that means early in the morning, when people are arriving at work and it's 7 or 8 a.m., the outdoor air temperature might be in the high 50s, low 60s. That makes a lot more sense to cool that air down than it does to just recirculate the 70 degree air that's inside, right? If you're using a forced air system like a VAV, or even RTUs. So the energy code recognizes that and it's like, hey, depending on your equipment, it might make a lot of sense to have these controls so that when it is a cool summer morning and we know that your building is going to be in cooling mode, we actually bring in more fresh air than is needed because it's cost effective to do so. They do require extra controls and things like that. So if you use a total building performance method, which is a method relying on energy simulation, which I'll talk about at the end of today from 1:30 to 2:30, you don't necessarily need economizers, although they still might help you get there because they might cut down on energy costs. But there's certain rules about it doesn't make sense in every climate and in every situation. If you've got a very small zone, very small unit, the extra controls and extra airflow that you might get during a few summer days might not be limited. So that is the goal of the energy code. It's not to make your life miserable or to make you fall asleep when you're reading it at your desk. The goal is to try to make it cost effective. Like, what are measures that are going to save occupants money over time? So if you've got a capacity for equipment that is less than 1.72 million BTUs per hour, you don't need an economizer, right? And then if the system is operating less than half time, it's not even a half-time worker, you don't need the economizer. Or if it's a supermarket with open refrigeration, again, you don't need the economizer, right? Because it might not be cost effective. You are always welcome to go above and beyond, right? The energy code is a bare minimum. That is, like, as Jerry Peterson says, the worst building you can legally build. Okay. And if you have a heat recovery system, which we'll talk about shortly, again, you might not need an economizer. In 2024, and anytime that there's a new requirement, I'm going to put it in red and bold, like, be aware that if we adopt 2024, this is a new thing coming down the pipe for 2027. And if it's just a slight amendment to the 2018, I'm going to put that in blue. So this is not currently, this DOS is not a current requirement in Idaho's energy code. But if we adopt the 2024, then it will be. If you have a dedicated outdoor air system with multi-stage equipment that's smaller than that capacity, again, you will not need an economizer. Okay. Again, economizers are great for dry, cool to warm climates, right? Which Boise is in the summer. I will say there was one time where our lab did something called a digital twin with hardware in the loop, where we modeled a campus building in Moscow and had the controller kind of sitting on our desk, and we could log in and see exactly what was happening at the building in Moscow, and then connected the controller to our energy model so we could kind of play what if scenarios. And we realized that their economizer was not going on at all. And we were like, why is that? And we saw it was a cool morning. It was like 7 a.m. Moscow time. No, it was a little bit later than that. Maybe it was like 10 a.m. Moscow time. And we saw outdoor air temperatures like 55 degrees. Why aren't they pulling that air in? Instead, they were just recirculating, like, mostly 70-degree air, spending a lot of extra energy to cool that 70-degree air down to 55 when they could have just brought in more outdoor air. So we had the good fortune to be able to just play with that damper and say, okay, well, just open it up, bring in more outdoor air. We did, and then we watched in horror on the controls as all the offices started to heat up to like 80 degrees or something like that. And we're like, okay, this is a problem. So we shut it back off. Why was that economizer not working? Because the temperature sensor was stuck next to some rose bushes, which were getting hit by sprinklers and 55-degree water, not the actual outdoor temperature, which was like 80 degrees, right? When we did actually change the location of that, and we did the energy model and said, okay, how much would you actually save? It was over 12,000 a year in terms of the savings that they would get from energy costs by using their economizer versus just having it completely shut off by having it at the wrong location, which is, a student's tuition every year that now goes back into the university's pocketbooks, which is good. Okay, so when you have an economizer, there are certain requirements from IECC rather than just saying, okay, we put one in, we're good. We have to make sure that it can provide 100% outdoor air. So when it's convenient for your building to do it, bring it all in. Have damper controls So it's not this manual thing where somebody has to climb up on a roof and pull a lever, because that's just not worth it. And then it should have a high limit shut off, right? At a certain point, the outdoor air temperature is going to rise above what the indoor temperature might be. And we don't want to, again, waste energy by overcooling air that we don't need. And then we want to relieve our excess outdoor air. So the idea there is to not over pressurize the building, but kind of have like a relief outlet. And then make sure that our dampers aren't just, even if they're closed, still leaking a whole bunch of air, which might in effect cause a lot of extra heating that we might need to do in the winter when our economizer is off and these dampers are closed. But if they're very leaky dampers, then effectively we put holes in our ductwork and we're just bringing in extra air when we don't necessarily want to be. For future code cycles, okay, this is the red. This is be aware that this might be coming, not just for Idaho, but for any jurisdiction that is adopting the 2024 code, which is a lot of, well, Montana, potentially the major areas of major cities in Wyoming, where there's now going to be a requirement for interlocking controls of operable openings. In Boise, examples of this would be like 10-barrel or push and pour, where they've got the big garage roll-up doors. The idea there is we don't want to be conditioning a lot of, you don't want to open up the garage door on a hot day and have your air conditioner just like running out into the street. The idea is that you kind of shut off your cooling equipment for a little while as long as that door is open. You can still have it open. It's just you shouldn't be running your HVAC equipment as hard. The other requirement coming in 2024 is that if you've got zones with both humidification and dehumidification, there have to be controls to make sure that you're not doing both at the same time. Just making sure that you're not wasting energy in those zones. I don't know that we have a whole lot of zones like that in Idaho, but maybe if you're doing a particular manufacturing or you have equipment that needs to stay in a very particular humidity range, then this might apply. So know that might be coming down the line in 2024. Okay, so that's kind of economizers. I want to move into demand control ventilation. So this is when you've got a skunk in the building and you're not shooting the skunk or fencing it in, that you're just providing an alert that, hey, something's wrong, something's smelly, let's do something about it. And when we don't have a skunk in the space, we don't need to bring as much fresh air in, right? So for spaces that have a lot of occupants, we require this kind of demand control ventilation so that you're not bringing a whole lot of fresh air into a room that is empty, essentially. Spaces, I need to duplicate that. I did mean to show that that does change slightly in 2024. The requirements get a little bit more strict where we need demand control ventilation in more spaces that have fewer occupants. Partly control costs have come down, so it's easier to put in. So this is, your rooftop unit, any sort of unitary equipment serving a zone. If the zone is, well, previously bigger than 500 square feet and it's got a lot of people that could be in there, when people aren't in there, it's just gonna shut down, right? Because the building doesn't need to breathe. It's only the people inside that do. Okay. All right. Demand control ventilation is also required for a place that has an economizer or automatic outdoor air dampers, or outdoor air of greater than 3,000 CFM. One thing that I think is helpful for getting these ventilation requirements correct as you go through the design process. Sorry, I was kind of freaking out. I think this piece of paper is on there. One thing that's helpful is to kind of go through the logic tree that is laid out in the IECC. To do that, you need to know what you're putting in. So if you have your design as an engineer and you know, okay, I know how I'm handling my ventilation. I know whether or not I have an economizer. I know the type of dampers that I have, and I know how much outdoor air I'm bringing in for each zone. What you can do is kind of have those in front of you, and then on another screen have, okay, these are the potential requirements. And I can just say, okay, I have no economizer in this zone. I've got no automatic dampers, and I've got, low outdoor air requirements. I don't need to worry about demand control ventilation. Great, I get to just move on, okay? It's far better to have all that information and kind of go through this checklist all at once, rather than having to kind of check after the fact of like every single time, oh, how much was in that zone? Do I need it there? I'm sure with spreadsheets and AI tools, you can automate a lot of this to kind of guide you through the energy codes. Like you definitely want to use your own brain and check it at the end. But it is helpful to kind of have this information at hand while you're going through the code to make sure that maybe you don't need a demand control ventilation, or maybe you do. And if you do, then you need to make sure that you are specifying that. There's also a lot of places where demand control ventilation doesn't make sense financially. So if you have energy recovery, great. We're going to be harvesting a lot of that heat. We don't have to worry about reducing our outdoor air as much, right? Because we're not losing as much energy. We're recovering some of it. If you've got a multi-zone system without DVC, again, it's going to be a lot of extra controls to put in demand control ventilation there. It's probably not worth it. If the outdoor air is less than, in 2018, 1,200 CFM, and in 2024, less than 750 CFM, again, you don't need demand control ventilation. It's just too little outdoor air. It's just not going to make sense. If your supply air minus your makeup air is less than 1,200 CFM, again, you don't need it. And then if you've got process load ventilation, like in a warehouse or something like that, you don't need it. And if you use that indoor air quality procedure that I was talking about earlier, where you are doing some indoor air quality scrubbing, you don't need to use demand control ventilation. So again, just kind of follow through the logic tree before you freak out and say, I need DCV everywhere. You might not. So make sure that, if you have any of these exceptions, you don't necessarily add in extra costs. It will, hopefully, if functioning, save energy. But is it going to be cost effective for your client or not? If you've got one of these other systems in there, it might not be cost effective, so you can save on some capital costs there. Now, what about energy recovery ventilation? This varies based on, I didn't put in all the requirements that you see from code, but it varies based on the percentage of outdoor air that you're bringing in. And how often that building is operating. So for an office, I hope nobody is sitting at their desks more than 8,000 hours out of the year. We have a total of like 8,760 hours each year. So this would be working like 23-hour days. Hopefully that's not the case in an office building, but it will probably be the case in care facilities, apartments, things like that. So in climate zone 5B, if we're in an office or something that is operating less than 8,000 hours out of the year, this is most of the state of Idaho, there's no requirement for ERVs. For climate zone 6B, some of the colder parts of our state, there is a requirement of having energy recovery ventilation if at least 80% of your airflow is coming from outdoor air. The less outdoor air you're bringing into the space, the less you might need energy recovery ventilation. So actually, for example, if you're using like 60%, you're mixing 60% outdoor air in the space, and the rest you're just recycling, then you only need ERVs once this is at 3,500 CFM. And if you have, say, just 10% outdoor air just for ventilation, and you're mixing that, you're recycling a lot of the indoor air. At that point, what was it? It was like 26,000 CFM, which would be like a huge auditorium or something like that. It's rare that you need that much outdoor air, right? So the idea is that the energy code is kind of seeing whether it would be effective or not. And the less outdoor air you're bringing in, the less there's a requirement for energy recovery ventilation. Okay. Now, when this is operating more than 8,000 hours out of the year, you've got some poor load chained to their desk and they're working 23 hours a day, right? Then you've got much lower airflow requirements, like even 80 CFM. If you've got, say, a dedicated outdoor air system where 100% of the ventilation air is coming straight from outside, it's going to be operating so much that it makes sense to have an ERV where you're kind of recycling some of that heat. In climate 6B, which is colder, think Idaho Falls, Salmon, Idaho, any zone that's got 40 CFM or more, you're going to need an ERV. Now, if it's not a dedicated outdoor air system and you're just kind of mixing in some fresh air and you're recycling most of that air, again, you only need ERVs at super high outdoor airflows of 2,500 CFM or more. Remember that calculation that I was doing on like how much fresh air does like a 2,000 square foot home need? It was about 90 CFM. So 2,500 CFM is a whole lot of people in one place. So you probably aren't going to need it if you are using, say, rooftop units or a VAV system that's not bringing in a lot of fresh air. But if you have a dedicated outdoor air system and a VRF or heat pumps, you are probably going to need an ERV if it is occupied most of the year. Okay. So just think residential, and I'm using DOS, I'm probably going to need an ERV. And it just makes a lot of sense financially and energy-wise when you start kind of doing the numbers. Now let's look at 2024. There are new requirements for non-transient dwelling units, apartments, right? There is a certain effectiveness that is required. You can't just stick in an ERV and say, hey, I'm capturing 10% of the heat, I'm good. It has to capture at least 60% of the heat leaving the building from that airstream and transfer that to the incoming airstream at the design conditions for heating. In Boise, I think those design conditions are around 9 degrees Fahrenheit or so, pretty cold. Or instead of an ERV, energy recovery ventilator, you can get an HRV or sensible heat recovery of 65% at 32 degrees Fahrenheit. This for Idaho is probably the target that you're going to be trying to reach. This is going to give you a lot more range in equipment that you can specify. This is probably going to be effective, but maybe overkill. There can be an argument for using a super high efficiency ERV where it's like at 85% efficient at design conditions in cold climates. But again, that's for a high performance building. Energy code is not everybody needs to be net zero. Energy code is baseline building. So for that, you need an HRV of 65% effectiveness at 32 degrees Fahrenheit. So if it's freezing outside, if it's 32 degrees and 70 degrees inside, we're going to end up at bringing fresh air in closer to, say, 50 degrees, right? Because we've got 65% transfer from one to the other. The other requirements that we have is parking garage ventilation controls. We don't need to ventilate all garages all the time. So you don't even need controls on garages with less than 22,500 CFM of exhaust. Or if your ventilation to horsepower ratio of your fans is larger than this here. It's kind of more on the technical side, but just know that just because you have a garage doesn't mean you need to have all these fancy controls. It really depends on how big it is. In 2024, though, there are additional requirements. One is that you're going to need a separate ventilation and control system for each parking garage section. They define parking garage sections as it's got to be like fully walled off. One car can't get from one section to the other section, right? They're kind of isolated units. It can be multiple floors, but if you've got a building and for whatever reason, you've got the parking garage split into two halves, or the basement is split into two halves, right? Then you need a separate ventilation and control system for each enclosed parking garage section. And the controls that you need to put in is to be able to reduce the fan airflow to either 0.05 CFM per square foot and 20% or less of fan capacity. Essentially, if people aren't moving their cars in and out, if there's not a lot of fumes, you don't necessarily need to have your fans running at full blast. Right? The other requirement is on the fan motor demands being less than 30% or less of the design draw at 50% per flow. So it's essentially just trying to say, okay, we know that we need to ventilate garages, but we don't need to ventilate empty garages. So you have to have some sensors there, and the sensors have to actually do something to control the fans to make sure that they're just not running full all the time. Okay. There's also some requirements just generally for when the building is in cooling mode, that we shouldn't heat our outdoor air beyond 60 degrees Fahrenheit. I won't talk too much about that. And then there's some also separate kind of hotel controls as well. This is group R1 with 50 or more guest rooms. There has to be a 30-minute shutoff. Essentially, we're not pulling fresh air into the hotel room when nobody's there after they've been absent for 30 minutes or longer. In IECC 2024, we're now reducing that to 20 minutes. And then you can do just like a 1 hour purge per day rather than having it kind of constantly ventilated, kind of just recycle all that heat all at once for 1 hour, and then otherwise don't need to bring in as much fresh air if it's just a vacant room. I did want to talk a little bit, this is more on the residential side, but the potential ventilation and heat recovery requirements that might be coming to Idaho. The IDL simulated a typical home, and we looked at the code changes from 2018 to 2024 to see, are these cost effective or not? We looked at the change in window U factor, the change in ceiling insulation, air tightness, and then the heat recovery is the one that I want to focus on here. So in climate zone 5, in the residential area, there is no HRV requirement, right? And in 2018, there's no requirement in climate zone 6 either. Once we hit the 2024 code family, At that point, they do start to require HRVs in climate zone 6 in those kind of cold regions because they think that for most of the country in climate zone 6, HRVs start becoming cost effective. We looked at that for an example in Salmon, Idaho, a 2,000 square foot house. And how much is it actually going to save that family per year to have an HRV? I get very interested in kind of energy costs, and that's part of the mission of the Northwest Energy Efficiency Alliance is to make sure that energy is affordable. Idaho has some of the lowest energy prices in the country in terms of both electricity and natural gas. But in Salmon, there's no natural gas line. So you have to have either propane or you're using electricity for your heating. So that has some of the highest costs in the state. But we found that modeling an HRV only saved about $132 per year. Because the way that we ventilate most homes in Idaho is we just kind of put in an exterior pipe from outside into our return duct line and hope that it provides the ventilation that we want. If you actually run the calculations, though, it's not pulling in the code minimum. It's legal in Idaho, but if you actually measure the amount of CFM that's being pulled anytime the furnace is on, it's much lower than that constant ventilation rate of, say, 90 CFM or something like that. Instead, we're pulling maybe 60 CFM and only when the furnace is running, not the rest of the year. So if you actually had it running, if you had full ventilation in the home, energy savings would be closer to $500 per year. So it might pay that HRV back within 2 to 3 years. But it doesn't make a lot of sense compared to how we build homes right now. The payback period on this is going to be very long. So that amendment was actually, or that requirement was struck in the code discussions. So even if Idaho adopts the 2024 code, on the residential side, no HRVs are going to be required in climate zone 6. Partly because it's tough to get installers out. People still aren't super familiar with HRVs or ERVs. It is legal, to not have an HRV and to just do a central fan integrated system where you're just kind of piping in some outdoor air, but you don't have any like fan controls on it, and you just run your bath fan or a kitchen fan and hope that it's pulling in enough fresh air. That is legally permissible. Is that morally defensive from a design standpoint by not giving these families enough fresh air? I find that I will just say there is the oath of the engineer that's kind of like the Hippocratic oath. And I think that we do want to focus not just on the bottom line of energy costs, we also want to focus on health. I'm very attuned to energy costs. There's the US Census Bureau does a pulse survey every month where they look at how are people spending money. And 1 in 5 Idaho families last month either did not buy enough groceries or did not buy medicine in order to pay the utility bill, or they just couldn't pay a utility bill at all. That's 20% of the population, hundreds of thousands of people. So it's a real issue, right? And I understand the goal of limiting construction costs, but we also have to think long term about energy costs for people. It's not just providing them a house; it's providing them kind of a way of living, so that they don't have to give up food or medicine in order to keep their place comfortable and lit. And I would also say well ventilated, right? That has a serious impact on our health. I think more and more we're becoming aware of the health impacts proper ventilation. All right, so got just a few minutes left. What are the takeaways from this? One, start with what you know about your design. If you know the zone sizes and ventilation loads, have that in front of you on one screen while you kind of go through the different requirements in the energy code, or even better, build your own spreadsheet/AI tool to check whether you need economizers, demand control ventilation, parking controls, right? And just make sure that maybe you don't need all that extra equipment or extra controls if it's not applicable. The other thing is minimize ventilation by targeting the pollutants. What are you doing with the skunks? Are you removing it, containing it, alerting that there's something happening? Are you just bringing better airflow through? And consider using the indoor air quality procedure as opposed to the ventilation rate procedure. Is it good to like bring less fresh air into a space and just scrub it more? Again, that's a design question that gets more into ethics and costs. I'm not going to give you the answer for that. Just know that it is an option available to you. And then if you do have economizers, make sure that you don't put the temperature sensor in a rose bush, and make sure that it's actually working correctly. And then if you need to specify demand control ventilation and energy recovery ventilation, make sure that they're effective, particularly in a cold climate. There's a great resource, betterbricks.com, on dedicated outdoor air systems, case studies in this region, in the Northwest, the inland Northwest, looking at rural schools in Montana and Idaho and Eastern Washington, and actually showing the dollars that these systems are saving. They also have partnerships with different equipment manufacturers, so you can find not just these theoretical magical units that might exist in Europe but aren't here available in Idaho. They've got a list of equipment manufacturers that supply here in Idaho that meet those IECC requirements. And then last, if you're trying to just do the simple thing and meet energy code and provide help, I would strongly recommend doing some performance modeling and using a dedicated outdoor air system. And that way you are going to limit the number of controls and headaches that you might necessarily need to navigate. A lot of those requirements kind of go away if you use performance modeling and dedicated outdoor air systems. So that's what I've got for you today on ventilation systems for commercial buildings, but I want to make sure that there's an opportunity for questions. So audience, do you have any questions on kind of commercial ventilation controls? All right. There's something in the chat, Dylan?
I'm watching the poll.
Okay. Oh. Any other questions? I see that a few of the students are starting to trickle in for class, so Dylan's going to be taking over shortly. But we're good to go on commercial ventilation and looking at 2018 versus 2024. Again, if you have questions on any of this, feel free to reach out to myself, the Code Collaborative, and highly recommend looking at other NEO resources like betterbricks.com for case studies.